Hello, everybody, and welcome to the session on data structures and algorithms hosted to you by Google Developer Scholars Club here at VIT. So, today we're going to be talking about data structures and algorithms as a whole, why it's important. We're going to be discussing some basic data structures and generally learning about this subject that's so important to computer science. So, first, we start with what exactly are algorithms, right? Algorithms are basically a step by step procedure for solving problems. You have some input and you want to get some output. And the algorithms is basically the step by step procedure that you would use to solve problems, to solve that specific problem. And we can see here in a small example, a very basic example of writing an algorithm to find the largest number in a list of numbers. So we can see here what are the steps that this problem requires. We start with the first number in the collection and we assign it to a variable, which I've currently called largest. So now we are taking the next number and we compare it with the current largest variable. If it's larger, then we update the largest variable to that specific number. Like that, we continue steps 4 and 5 until all the numbers have been compared, and at the end, we return our largest number. So here's an example. We have a list of numbers here, list of 8 elements, and you can see the first element 5 is our largest element for now. And this value I, which is the iterator, is going to check each of these values and see if it's larger than the current largest value. And if it is, then it's going to set that largest value to I. So as we can see, 1 is not greater than 5, so there's no change to the largest value. 8 is larger than 5, so now the new value of largest becomes 8. Similarly, 10 is larger than 8, so the new value of largest becomes 10. And as we go through the rest of the values in this list, we can see that none of them are greater than 10, so the value of largest does not change at all. And at the end, when we've reached 3, we see that the value of our largest element is 10, and that is the element that we return, and that is our answer. So we've understood what algorithms are. So what is data structures now? And DSA stands for data structures and algorithms. Basically, data structures are a different ways of organizing and storing data. So each data structure has its own structure, strengths, its weaknesses, and its efficiencies and inefficiencies. So in DSA, algorithms are used to solve the problems efficiently, and data structures are used to hold data in appropriate manners and efficient manners. So we can see the classification of data structures here. They're classified into primitive and non-primitive data types. Primitive data types consist of integers, floats or decimal numbers, characters, and Boolean values or true-false values. Non-primitive data structures are basically built as a collection of primitive data structures. You have linear and non-linear. And within linear, you have two types. Static means that the size of that data structure is a constant. You can't change it, you can't make it bigger or smaller. It's a constant value. And an example of that here is an array. A dynamic data structure, on the other hand, is a data structure whose size can be manipulated. You can increase the size, you can decrease the size, and examples of those are linked lists, stacks, and queues. A non-linear data structure, an example is tree and graph. So what are arrays? An array is just an ordered sequence of homogeneous elements. In other words, the array can only hold elements of one data type. It can only hold integers or it can only hold floats, likewise. And Python arrays are basically just wrappers for C arrays. They're an extension of the functionalities of C arrays. So the type is constrained, it's specified at the time of its creation. You can't change it later. And they consist of contiguous memory locations, which basically means that they share a common border or they're together in sequence. So here we have a small code snippet that shows how you would create a basic array in Python. And this is how memory representation of arrays look, right? You have these numbers 100, 104, 108, which is basically the memory location. And the data being stored, you can see they're all integers, they're all of one data type, and they're all right next to each other. They each integer is 4 bytes, which is why it's 100 and then 104. And likewise, we can see that they're all stored in one block of memory. So that's why it's contiguous. So our next data structure is the linked list. And linked list, if you recall, is dynamic. You can increase the size, you can decrease the size. And it's basically a collection of node objects. And a node object consists of two different things. First, the data. And along with the data, it also consists of a forward pointer, which contains the address of the next element. And this linked list can be of two types. It can be unidirectional, and that's a singly linked list. You can also have a pointer to the previous node, and in that case, it'll be a doubly linked list. So how does a memory representation of a linked list look? You have a basic node here, and this node has a data value, which is 5. It has a memory location, 104, and this memory location points to the next node in that linked list. And similarly, the data value here is 1. Its memory location that it's pointing to is 248, which is another node. And like this, you can have multiple memory locations in the linked list. And so we find the middle node of our linked list, right? So what we want to do is we want to take a linked list as an input, and we want to return the value of the middle node. If the length of the list is even, the middle value will occur at length, like the half length. And for an odd length, the middle value will be length by 2 plus 1. And so one basic solution that comes to many people's minds, and it certainly came in my mind, is to traverse through the linked list and count the number of elements, and at the end divide it by 2, and then go to that specific element. If you have, for example, in this sample input output, you can see that there are 4 elements. So what one might do is that they traverse through this list, and they'd say, okay, there's 4 elements in this linked list, and 4 divided by 2 is 2. And so the second element, or 14, is our middle value. But there's actually a more elegant and more efficient way of doing this. And this is where algorithm comes into play. So our first approach was what's called the naive approach, or the simplest approach possible. You traverse through the linked list, divide the count of the elements by 2, and traverse to that specific node. But there's also a separate method which uses two pointers, the fast pointer and the slow pointer. And the fast pointer takes 2 steps at a time, while the slow pointer takes 1 step at a time. So you can see an example. We have a linked list here, and both the fast and slow pointer are currently pointing to this first element, number 5. And as we'll see, the fast pointer moves 2 steps forward to 8, while slow moves only 1 step forward to 1. And likewise, that step continues 1 again and again. And now the next to next element to this fast pointer is a null value. The linked list does not exist at that position. So at that, we stop and we take whatever the slow value is, and that is now our middle value in our linked list. So our next data structure that we're going to learn is stacks and queues. And again, these are linear data structures. They're dynamic. Their size changes. So stacks follow the last in, first out ordering. This means that the last element added is the element on the top, and the first element added is at the bottom. And the last element is the first one to be removed. You can only remove it from that direction. And a queue is another linear data structure which stores it in a sequential manner that implements the FIFO ordering, or first in, first out. And a small animation to display this, you have stacks, right? And you push an element, and you can see that they're stacking on top of each other. So when we want to pop an element, the name or the last one to come into our stack that is the one that will be popped. And that is how our stack can be manipulated. A queue follows first in, first out. So, as how queues work in real life, first person to the line, second, third, and the first person leaves first. Hi. Sorry, there seems to have been internet connectivity issue. I'm back now. So I'll go through this problem again, right? We had started on how to implement a queue using stacks. And so we can see that uh, the main difference between queues and stacks is dequeuing an element. Uh, Enqueuing an element or adding the element, there's basically no change. You just add it to the top. But when you wish to remove an element from the stack, you have to remove it from the top. While from the queue, you have to remove it from the bottom, which is basically the first element. And in order to implement that, we're going to be making use of another stack. So we can see here, we have a stack of A and B. And if we want to enqueue an element, we don't need to make any changes. We just simply add a new element C. But now if we want to dequeue an element from this stack, technically, according to stack functionality, the first element will be C. But if we want to implement it as a queue, we need to remove A, not C. So what we do is we make use of the second stack over here, and we basically transfer all of the values from our first stack to our second stack. So C, then B, and now we can remove A. And once we remove A, we transfer all our elements back to the original stack, B and C. So That brings an end to linear data structures. And now we're going to move into the more non-linear data structures, which, if you recall, was graphs and trees. So a graph is a set of nodes that are connected to each other in the form of a network. And we're going to first define the two basic components, right? We have a vertex and we have an edge. And the vertex is basically your data, right? And the collection of vertices together forms one graph. An edge is the link between two vertices. It can be unidirectional or bidirectional depending on different graph functionalities. So, one question here, right? How do we check if a path exists between two vertices? So, here we can see a unidirectional graph. We have a source value and we have a directional value, a destination value, my bad. And we want to return true if a path exists from the source to the destination. And we can see our sample input here, a graph which has values from 0 to 2, 0 to 5, 2 to 3, 5 to 3, 5 to 6, 3 to 6, and 6 to 7. Our source here is 0, our destination is 7, and we want to check if a path exists. Looking at this graph, we can see that obviously, yes, a path does exist. But how do we implement an algorithm for the same? How do we let the machine figure it out for itself? And the way we're going to do that is that we're going to traverse through this graph and we're going to see if our destination element comes up. So the way we're going to traverse through this graph is we're going to start with our source value, which is 0 over here. And we're going to add it to this queue on the side. And we're going to say at each step, we're going to remove that specific element and add all of the elements connected to it. So our first step, we have 0. We're going to remove 0 and we're going to add 5 and 2 because those, as you can see, they're the two elements connected to 0. And one by one, we're going to make our way through this graph and we're going to see if 7 shows up in the end. So let's continue. We have 5 and we remove 5 and you can see 5 is connected to both 3 and 6. So our queue now becomes 2, 3, and 6. Now, one important thing here to note is that when we remove 2, the only element it's connected to is 3. But 3 already exists in this queue. So we're not going to add it again. Instead, we're just going to remove 2 from this queue. And our next step will be 3, comma 6. Similarly, 3 is only connected to 6. And since 6 is already in the queue, again, we're not going to add it. We're just simply going to remove 3. So here we get 6. And now 6 is connected to 7. So when we remove 6 and add 7 to our queue, then we can say that this destination does exist and that a path does exist from 0 to 7. So now what are trees? Trees consist of vertices and edges that connect them. So they're hierarchical data structures, which basically means that they're similar to graphs, but they're acyclic, which means that there's only one path between any two nodes. And there's a number of terminologies associated with trees, and we can see them over here. So the top of this tree, A, is the root node, right? And within each tree, there's a parent node, child node, sibling nodes, etc. And what they basically are is that a child node is any node that is basically descended from a different node. So we can see B is the child of A, C is the child of A, likewise D, E, F, all are children of B. And B is then in turn the parent node of D, E, F. A is the parent node of B and C, and so on. And because B and C are both children of A, they both are assigned the terminology of sibling nodes. And similarly, D, E, F are all sibling nodes to each other. A leaf node is a node that doesn't have any child nodes. So, for example, this G over here is a leaf node. It has no children. So that's why it's called a leaf node. Similarly, H, F, and D all would be associated, all would be called child nodes. Now, an ancestor node is basically a node that is like above it through multiple levels in a sense. So A, for example, would be an ancestor node of D, E, F, G, and H. So it's basically above it, it's connected through multiple levels, not just through one. It's above the parent node. And so that's why B would also technically be an ancestor node to H. Now, two terms, one is depth and one is height of the node. So a depth of the node is the distance or the number of edges that it takes for us to go from the root node to that specific node. For example, the depth of the node B would be 1 because there's only one edge connecting A to B. The depth of D would be 2, E2, F2, and H would be 3 because we need 3 edges to go from the root node, which is A, till H, which is the node that we're looking for. And now the height of the node N is the longest path for that a node has to take to reach the leaf node. So for example, the height of this node over here, C, would be 1 because the leaf node is G, right? So there's only one edge needed. And so that's the height of C. But for B, you can see that there are multiple options it has. It can the nearest leaf nodes, sorry, are D, H, and F. But since we're taking only the longest path, that means that the height of B is 2, not 1, because the longest path to a leaf node is H over here, which is two edges. And so the height of A is 3, because the longest path to a leaf node is through B, E, and H. And that takes us uh, to the leaf node over here. So binary trees. What are binary trees? We saw trees earlier, and a binary trees is basically the same thing, except that they can have only two children at max, either 0, 1, or 2 children. That's all. And there are different methods associated with traversing them, and we can see them over here. First is pre-order traversal, in-order traversal, and post-order traversal. So we're going to go through examples of these, right? And we can see over here that considering this is a binary tree, right? You can see that each element has a maximum of two children. A has B and C, D and F, G and H, and some nodes like G have only one child, K. And so we can see the different types of traversals, right? In order traversal means that we first take the left node, then the root node, and then the right node. And so this basically means is that for this tree, we move left, left, left all the way here until we can't move left anymore. We take I, which is the left node, and then the root node D, and its right node J. And then we continue. This D is the left node, B is the root node, and F. And this entire section is the left of A, which is now the root node. And you can see over here, that is the order that we go through. And after A, we take the left path here. Now, over here, since G is technically the root and it has no left child, then we don't take anything here. And so we take G and then K, which is the right node. And then this entire thing is the left node for C, and then H, which is the right node here. Now, pre-order traversal means that we first take the root, then we take the left, and then we take the right. And this changes things up a bit. So first we take A, then we take B, which is the root node, and then D, and then we take the left and right side. So left is I and J, and then the right side here is F. And now the right side for A becomes this entire thing, where we first take the root node, which is C, and then the root node left side G, and then K, and then H. Post-order traversal means that we take first the left side, then the right side, and then the root node. So we first start with I, all the way on the left here. But now instead of taking D like we did in order, we take the right node, which is J. And then we see that it's left, I, then J, and then the root node here, D. And then similarly left, right, which is F, and then B. And now this entire thing is the left section. And now we look at the right section. So in the right subtree over here, we can see uh, since G has no left node, we automatically take K, which is the right here, and then G, which is the root, and then G, H, and C. And after both left and right subtrees are done, after that we take A, which is our main root of this binary tree. And with that, we come into why DSA is so important to learn. And the reason it is because whenever you're performing any computer functionalities, you don't have an unlimited amount of space, which is memory space, and you don't have unlimited time. Whenever you're coding something in, you want to make sure that you're as efficient as possible, both with your time and your space. It's not something that can be wasted, considering that many users would be using it. You might be using lots and lots of data, and you don't want simple operations to end up taking a long amount of time, or you don't want to be wasting money buying more memory space even though it's readily available. It's a waste of costs. So it's really, really important that you understand how to use more efficient algorithms, more efficient data structures, and you're able to understand why they work and how they work, so that whenever you're creating something, you end up creating its best possible version. And it has multiple uses, right? Whether we're using it in standard apps or servers, real world problems, machine learning, anything that is used on our system requires in a thorough knowledge of DSA. And that's why it's so important in the technical hiring process, because any company looking to hire you will want to know that you understand how to make things work efficiently, and you won't be costing them a lot of time, a lot of space, and you won't be costing them more money, right? So that's why it's extremely important to understand and learn DSA. And you can see here, these are a number of resources, a number of courses or websites that you can go through, and you can see how DSA works, right? And you can understand it for yourself, and hopefully it can guide you on your journey to becoming a computer science developer. So thank you, everyone. I hope you all learned something from this session, and I certainly had a great time making it. So thank you.